everyone. So let's sorry for late notification about the class today because I only get I know that it is a requirement of school that we should have class today, so I can't do anything to that. Let's review what happened last night. So last night we studied the elementary row transformation and the elementary column transformation. So why we care about those two kinds of transformation? Because we want to study the row space, namely it is all possible linear combination of row vectors, and we also want to study the linear relation of columns. So linear relation simply means an equation that contains scalar multiplication and the sum. So the reason that we want to study elementary row transformation it is because the elementary row transformations does not change the row space or linear relations on columns. And also, respectively, we have the elementary column transformation, which does not change the column space and linear relations of rows. Okay, and after we say something about that, we want to make everything rigorously. So which I mean is that I want to make everything into the equalities. So in this way, we have talked about how to realize the column transformation and row transformation by matrix multiplication, and those matrices that realize such kind of transformations is called the elementary matrices. So elementary matrices is obtained from the unit matrix by doing the same thing on the unit matrix. For example, if you want to add like this matrix, this 1, 1, 1 is an elementary matrix. So what does that mean? So as you can see, this 1, 1, 1 is multiplied on the left of your matrix, right? So it means the row transformation, and then the next step is that you think about how do we get this kind of matrix by row transformation from unit matrix. As you can see, because of the one right over here, so the way we get this matrix is by adding the second row of the unit matrix to the first row. So in this way, we observe that this matrix when multiplied on the left actually means adding the second row on the first row. So when you multiply this matrix on the left of this matrix, what is the result? Anyone? What is this? What's phone number? 7745. Yeah, 7745. Yeah, it is because we adding the second row of those matrix to here. Or you can also check by the you can also check by the general rule of matrix multiplication that this number should be this times 1 plus this times 1, and this number should be like this, and this number should be like this. But this kind of multiplication may cost you some time to actually compute it out. And if you know the exact meaning of this matrix, you can compute in easier way. So how about this matrix? How about if I multiply this matrix on the right? So what are those four numbers? Are you ready? Yeah, 3549. So why is that? Because this matrix is an elementary matrix, and now it is multiplied on the right. And when you multiply an elementary matrix on the right, it simply means you are doing column transformations of this matrix. And then to know which column transformation we made, you only have to see how can we obtain this matrix from unit matrix by column transformations. So it is clear that because of the one right over here, so we can obtain this matrix from unit matrix by adding the first column to the second column. So this matrix actually will multiply on the right, means you're adding the first column to the second column. So, and you do the same thing right over here. So you're adding 3, 4 to the 2, 5. So, and then it becomes 3, 5, 4, 9 right over here. Can everybody see the blackboard? Okay. Okay. So how about this one? What is this equation equal to? 6, 2, 3, 4, right? Yeah. It is because this matrix multiplied on the right. It simply means you exchange the first and second column, and then you do the same thing to here. So it's 6, 2, 3, 4. What is this?
2 rows.
Yeah, switch rows. So result is 4, 3, 2, 6. So how about this matrix? 10. 2, 5. Yeah, 2, 5, 14. 2, 5, 14, 2. Yeah, it is because this matrix is multiplied on the right of this matrix, right? So on the right means column transformations, and how do we obtain this matrix from unit matrix is by multiplying the first column by 2. So when multiplying this matrix to that simply means you multiply this matrix by 2 on the first column. So the result is 2, 5, 14, 2. So those are elementary matrices, and how do we use them to calculate something. Okay, and after all of that, we have studied the reduced row echelon form, and there are 3 criteria of reduced row echelon form, which you can actually find on the notes because I don't want to write it again. And I actually tells you that those 3 kind of properties have each of the properties have something to do with one kind of elementary row transformations. Like the first one says that each non-zero rows have the leading coefficient is 1, which is right over here. So those ones are called leading one, or pivot. It is just some word. And this rule deals with the row multiplication, right? So it means that this is the easiest form that you can reach by the row multiplication. Which I mean is that if you do any row multiplication, then you cannot keep those leading ones. Those leading ones might become leading 2 or leading 3, which is not what we want. And the second one said that for each leading one, and the following the rows below this leading one must have the leading one further to the right, which means that it should be like of this form. And this law has something to do with this law is related to the row switching, right? So it means that your switching is done so that you can reach this kind of form. Which I mean is that if you switch this reduced row echelon form, then you cannot keep this property. So this means that you have already done enough row switching such that it reduced to the easiest form. And the third one has something to do with the row adding. The third one says that for each leading ones, it already clean up all its columns, like things over here. So it says that for this leading one, the other entries of the columns must be 0. And for this leading one, all the entries of this column must be 0. And this leading one are the same, right? And this has something, this says that your row adding is actually done. It's actually, you did enough row adding such that it becomes the simplest form. Because if you do row adding on this row echelon form, you can't keep those 0, right? If you want to add this row multiply twice on that, then this 0 will go away, and this will become 2. So actually, those three properties says that you did enough row multiplication, you did enough row switching, and you did enough row adding such that they reduce everything to the simplest form. So this is a reduced row echelon form. And actually, because as we said earlier that the row transformation does not change the row space and the linear relations on columns. So which means if this is a reduced row echelon form of A, we always denote it as reduced row echelon form of A, where A might be some matrix. So what is the relationship between the reduced row echelon form of A and A? It is clear that actually they are not the same matrix. So which kind of property do we keep, or do we actually keep it? So because the row transformation does not change the row space and the linear combination and the linear relation on columns, so actually the row space of A is actually equal to the row space of the reduced row echelon form of A. Because the reduced row echelon form of A is actually obtained by doing row transformations. And also the linear relations on columns of A also are also the same with the linear relations on columns of reduced row echelon form of A. So linear relations on columns of A actually are the same with linear relations on columns of reduced row echelon form of A. So those are the usage of the reduced row echelon form. And then at last we give some example of how do we know whether a vector actually lies in the row space of this of the matrix, and then we using an example to talk about that. So let's kind of review the example, because last time I remember some of you guys asked me about these questions. Okay, so previously, what we did is we reduced this matrix, right? 1, 2, 1, 2, 7, and 2, 4, 2, 6, 18, and -1, -2, 0, -1, -3. And then we reduce that to the 1, 2, 1, 1, 2, 2, 1. And then now if I ask you a question that if this is A and this is a reduced row echelon form of A, right? And now I just want to ask you to actually, if I suppose that here are some row vectors, which is 2 and maybe some variable x, and maybe 3, 1, y. If I suppose that this vector actually belongs to the row space of A, can you figure out what is x and y? let me put this question. So what is x and y? So what is x? 4. Okay. So what is y? Let me 2 plus 6 plus 2. Okay, yeah. Y is 10. Okay, so how do we know that? Everybody clear? Or not? Okay, as you can see, because this row vector, I assume that it is in the row space of A, which means this vector should be a linear combination of those three vectors, right? But actually, any kind of linear combination of those three vectors is actually the same as, say, the linear combinations of the row vectors right over here, right? So in order for this vector to belong to the row space of A, it's actually the same as asking as requiring that this vector belongs to the row space of reduced row echelon form of A. So then actually we know that the condition can be changed as this vector belongs to the row space of the reduced row echelon form of A. So which means that this vector must be a linear combination of those three row vectors, right? And because the linear combination of those three row vectors gives you this kind of vector, right? So it's pretty like, so what is the linear combination of row vectors? It simply means that you multiply each vector by something, right? By some coefficient, and then add all of something, question mark multiply this, and then question mark multiply this, right? And question mark multiply this, and then you sum it up, right? You sum it up, and then what you got is 2x 3, 1, y, right? And because as you can see, here it's 2, right? And all of those are 0. So something times 1 plus whatever, this is 0, because anything times 0 is 0, right? So because you require that this sum has the property that here is 2. So the only thing that this question mark could be is 2, right? So we need 2 right over there. Okay, and then you look at 3 over here. Because in the sum, those entry, when you sum up, it should be 3. So as you can see, because you have 0 right over here, so there's nothing to do with those two numbers. And then the only coefficient that this could be is 3, right? Or this will be another number. Okay, and look at this one. So by the same reason, this question mark must be 1, right? So this means if this is a linear combination of those 3 row vectors, the only coefficient it could be is 2, 3, 1. And if 2, 3, 1 are the coefficient, then you just sum it up right over here, right? So 2 times 2 is 4, right? And 2 times 1 plus 3 times 2 plus 1 times 2 is 10. So that's why x is 4 and y is 10. So everybody clear? Yeah, I think this should be easy enough if I explain this one. Okay, but remember that I only know this vector is in the row space of reduced echelon form of A, and is in the row space of A. But the coefficient actually are not the same if I write this vector into the linear combinations of row vectors of A. I'll say it again. Okay, so this 2, 4, 3, 1, 10 is in the row space of reduced rational form of A, and it's also in the row space of A, but actually the coefficient, the coefficient right over here are actually not the same. What I mean is that this vector is actually, if I name it as R1 tilde, R2 tilde, and R3 tilde, and if I name it as R1, R2, R3, right? So what I know is that 2, 4, 3, 1, 10 is actually equal to 2 times R1 tilde plus 3 times R2 tilde plus 1 times R3 tilde, right? But actually, I don't know how, I don't know coefficient right over here. Right? What I mean is those coefficients are actually not the same. And how do we find those coefficients is by actually rewriting this R1 tilde in terms of the linear combination of R1, R2, and R3. So, but we only know that definitely it is a linear combination of those three. So in one sentence is that the row transformation keeps the row space, but does not keep the linear relations on rows, because it only keeps the linear relations on columns. So that's my point over here. Okay, so this is a usage of the reduced row echelon form to study the row space. Actually, if you got a random row vectors, you can use reduced row echelon form to see whether it is in the row space or not. Okay, any question? Okay, I think it's pretty clear. So, okay, and then last time I also said that we can also use this reduced row echelon form to see the linear relations on columns. So what I mean is that the reduced row echelon form does not change the linear relations on columns. So actually, as you can see in this reduced row echelon form, the second column is the twice of the first column. So the same thing also holds here. The second column is the twice of the first column. And here the last column is 1 times the first column plus 2 times the third column plus 2 times the fourth column. And so the linear relations also holds over here. So everything up to now is clear. Okay. Then let's see how do we know that. Okay. And then let's use this. Now let's use the property that it keeps the column. It keeps the linear relations on columns to study the column space. Okay, so now I want to study the column space by the reduced row echelon form. But as you can see, actually, the column space of the reduced row echelon form are not the same as the column space of your original matrix. So how do we study the column space? So this is so actually the method of checking whether a vector in the column space by using the reduced echelon form is actually not the same of checking whether a row vector is in the row space of A. So how do we do that? Because as you can see, the reduced echelon form has the same row space of as the original matrix and has the same linear relations on columns as the original matrix. So instead of using this property, we can actually using this property to check whether a column matrix is in the column space of A. So let's make it more clear. So what does it mean by a column matrix in the column space of A? So suppose I have maybe a column matrix, maybe something over here, and this one belongs to the column space of A. Actually, what does this sentence mean? This sentence means actually this column matrix could be written as each columns of A multiplied by some number, right? So where I denote this A as C1, C2, and C3 until Cn, right? So actually, the method we use is that because as you can see, if this vector in the column space of A, then we have this kind of expression, although we don't know what is A1 to AN. But actually, this expression could be viewed as a kind of linear relations in those columns, right? So actually, this vector in the column space simply means you have a linear relations of this column matrix and those column matrix of A with those coefficients. So what is the method? I will show you an example of how do we check a column vector in the column space of A. So I'll erase this one. Okay, I'll use the arithmetic sequence example. So previously we read a matrix like 1, 1, 1, 1, 2, 3, right? And actually, I'm asking you guys whether a vector is a linear combination of those two columns or not. So let's just read random one, like any arithmetic sequence, for example, 3, 7, 11, right? And as a simple observation that this should be in the column space of these two because they are all arithmetic sequence, right? So how do we check it? Check that. We check it by this way. 1, 1, 1, 1, 2, 3, and we draw a dashed line over here, and then we write 3, 7, 11. And then now we do the same. We actually do the row transformation of all of that together, right? And reduce that to the reduced row echelon form and see what happened. Okay. So you actually the second row minus the first row, right? And then the third row minus 1 times the first row, and then you get 1, 1, 3, 1. Oh, this is 4, and this is 2, and this is 8, right? And then you just do it again, and then the last row minus 1, times the second row, what you get is actually 2 times the second row. Sorry. 1, 1, 3, 1, 4, 0, 0, and then also, and then you can do the last step is let's do it over here. Because we want to clear it over here. So the first row minus the second row, and then what you get is actually 1, 0, minus 1, and then it's 1, actually 4. Right? So what do you get? You get this kind of matrix, right? And because the row transformation does not change the linear relations on columns, so which means, as we can see, the linear relations of the columns is very easy to see, right? So you have the third column is equal to the first column times minus 1 plus the second column times 4, right? So let's call it the first column, the second column, and the third column. And then let's call those original matrix, the first column, the second column, and the third column. And then this linear relation actually tells you that the third column is equal to the first column times minus 1 plus the second column times 4. And then actually you know that 3, 7, 11 is actually equal to 1, 1, 1 times minus 1 plus 1, 2, 3 times 4. And then you know this vector is actually in the column space of A. Okay, so let's see an example. What if this matrix is not in the column space of A? So then what will happen? Okay, so let's just use a random one. Let's say maybe 1, 5, 10, right over here, right? And then intuition tells us that this vector is actually not in the column space of that, because it is not an arithmetic sequence. So how do we check that rigorously? What we will see is that, okay, so 1, 1, 1, 1, 2, 3, and dash line 1, 5, 10. And we can do the row transformation together, right? So, okay, the second row minus the first row, and the third row minus the first row. What we get is 1, 1, 1, and 0, 1, 4. What? Okay. 2, let me check. Okay, 2, 9, right? And then what you do next is you can use the second row to clean up all of that. So the first row minus the second row, and the third row minus what? Minus 2 times the second row, right? And finally, what you get is actually 1, 0, minus 3, 1, 4, and actually this is 0 and this is 1. As you can see, what happened? What happened? So as you can see here, 1, 1, minus 3, 4, 1. So this means whether whatever you do linear, whatever linear combination that you do on those two columns, it's impossible to make this column matrix, right? So which I mean is that let's denote it as C1 tilde, C2 tilde, and C3 tilde, right? what I mean is that C3 tilde is not equal to C1 tilde times A plus C2 tilde times B for any A and B. And what does that mean? Because the row transformations does not change the linear relations on columns, right? So this actually means the third columns originally, so this is the third columns, originally is not equal to C1 times A plus C2 times B for any A and B, right? For any numbers. So in this way, C3 is not in the column space of A. Okay, let's see actually what happens. Actually, how do we know that this equation is not true? It is because question.
Yeah, how did you do that very quickly? By just looking at the, initially without doing all this reduced relation form. Is that?
I did reduce relation form, right?
Yeah.
I clear up this and I clear up this.
Right. You said, but you said earlier that without doing this, you can.
Oh, because actually the question here is very special, because each columns of the matrix is arithmetic sequence, which is 等差数列. 等差数列. You know the word?
Yeah.
Okay. Yeah, because maybe. Yeah, arithmetic sequence. It means a sequence that each adjacent numbers have the same difference. Okay. Yeah, because it is an English word. Yeah. Okay. Okay. So this is a method of actually see how does when does the column matrix in the column space. Okay. So what's the next point I want to make? Okay, yeah. As you can see, it is not equal because this exceeding leading one, right? So this leading one is exceeded below this level. So that's why we can't combine them, because all of these coefficients over here is all 0, right? So no matter how you combine them, if this is a linear combination of those two, this should be 0. But this is 1, so that's why it's failed to be a linear combination of those two. Okay. Okay, let's think about these questions. Previously, I told you that we can use the reduced relation form to study the row space of A, if you give me any any row vectors, I can check very quickly whether it is in the row space or not. And now I also tells you that you can also use reduced relation form to study column space. So why don't we use the reduced column echelon form to study column space? Actually, we can, but as you can see, what are the advantages and disadvantages of using such two kind of method to study the row space? As you can see, actually, the first method is that you can study row space by looking at the reduced relation form. And the second method is that you can also study row space by using reduced column echelon form, which is pretty similar to this way. So what are the advantages and disadvantages? Okay, let's see. When you using the reduced row echelon form to study column space, or using reduced column echelon form to study the row space, the advantage is that the coefficient here is actually pretty clear. Like this is over here. You not only know that this vector is a linear you not only know that this vector is in the column space of A, but you also know the coefficient right over here. So that makes everything pretty clear. So you know the coefficient over here, and you know the coefficient over here. What is the disadvantage? The disadvantage is that when you are given a vector, you should do all the process from the original guy, right? You are given these vectors, and you are asking whether these vectors is in the color space of that, and then you put them together and do the reduced real echelon form together. So that means if you have a bunch of column vectors, you will put them all over here, right? And then it will actually a lot of work to actually do that, to see that. Okay, this is one way, and let's compare it to another method. So this is the disadvantage, and this is the advantage that we know the coefficient. Okay, so what is the advantages and disadvantages using this method? So the second method is to study the row space by reduced row echelon form and study column space by reduced column echelon form. So over here, this advantage is that you only have to do this reduced process only once, and over here, and then if you get any arbitrary vector, what you do is just by this pretty simple arithmetic to see whether this times this plus this times this is equal to the number over here. So if you have a bunch of row vectors, and it is very easy for you to check whether it is in the row space of that or not. You don't have to redo the process again, and you don't have to do the process with a bunch of row vectors. So this is the advantages of this way. And what is the disadvantages over here? The disadvantages over here is simply that those coefficients right over here is actually not the same as the coefficient right over here. Right? I'll put it. Those coefficients right over here are not the same as the coefficient over here. So those are the disadvantages of doing this way. So actually, if you transpose all of the matrix, you can study the column space by reduced column echelon form, or you can study row space by reduced column echelon form. All of that are actually due each other. Any questions of this part? Okay, so yeah, this is usage of the reduced relation form to study linear relations of columns and to study and to check whether a column matrix is in the is a linear combination of other columns. Okay, yeah. So far so good. Let's continue talking about how to find the inverse matrix. Okay, so as I said earlier, the matrix multiplication, you can in the matrix multiplication, right? Let me see which part should I erase. In the matrix multiplication, you have that AB is equal to C, right? And then this A, after multiplying this A on B, actually means some real transformations, right? So as you can see, when I'm doing those kind of steps, what did I do? I'm actually multiplying some matrix on those matrix, right? So to be clear, I'll just say, how can we write those process into equations? Okay. As you can see, this process just means that this matrix, let me see, this matrix 1, 1, 1, 2, and 3, 4, 8, right? This matrix should equal to this matrix, right? Should equal to this matrix 1, 1, 1, 1, 2, 3, 3, 7, 11 multiply the matrix that's corresponding to these two kind of actions, right? So this is R2 minus 1 times R1. So it's R2 minus 1 times R1. And then you do this, means R3 minus 1 times R1. Okay. And so this arrow actually means this equation, right? So it means if you do these two kinds of row transformation on this matrix, you got that matrix. Okay, and then you continue, right? And from this matrix to that matrix. So okay, so from this matrix to that matrix, you get 1, 1, 1, 0, 3, 4, 0. Let me write our new matrix over here. 3, 7, 11. 1, 1, 1, plus 1, and 1, 1, 1, plus 1 right over here. And then what you did over here is the third row minus 2 times the second row. The third row minus 2 times the second row. Right? Okay, and the last step is the first row minus the second row. So let me copy all of that. Okay. As you can see, all the process can be actually described by this kind of stuff. So, and if you multiply those matrices together, right? And what will you get finally? Let's check. Okay, you will get this matrix. 2 minus 1, 0. Minus 1, 1, 0. 1 minus 1, 1. Times 1, 1, 1, 1, 2, 3. And 3, 7, 11. So those matrix is product together into this matrix, like right here. So as you can see, we are doing row transformations. We are actually doing left multiplication by some invertible matrix. And then if we collect all those actions, actually we got a matrix. Those matrix is actually recording our process of row transformations. So which means this matrix is actually representing all of that transformations together. And if you multiply that on the left of that, it means to play the transformations that is recorded. And then the final result is like this. Right? So this is the invertible matrix. Why is that? Because each of them are invertible. So this is another point of view to see a row transformation. So how much row transformation you did, actually the thing that you did is actually left multiply an invertible matrix. So it's right over here. Okay, now let's write a statement.
How do you know how to transfer that whole thing into matrix?
How do I know? Right.
Yeah.
So because last course I tell that each row transformation corresponding to the elementary matrix, right? And this is by playing the same row transformation to the unit matrix. So actually, when you do the second row minus the first row, right, it's the same as left multiplying a matrix, which is obtained by the second row minus the first row unit matrix. It's right over here. This matrix means the second row minus 1 times the first row.
How do you know where to place the minus 1?
Where to place minus 1, right?
Yeah.
Well, if you do the same thing to the unit matrix 1, 1, 1, right? If you do the second row minus 1 times the first row, right? What will happen? It is the second row minus 1 times the first row. So it's like this one, right? So you do the same thing to the unit matrix, and then you will get which matrix you want. So this matrix means that you minus the first you minus the third row by the first row, and then all of that, right? Any other questions? Okay. So propagation for any matrix A, there exists an invertible matrix P. Such that P times A is the reduced row echelon form of A. Okay, so this proposition is very clear from the phenomenon we saw at this time. So what is the P? Actually, this P is actually the recorder. It's actually recording which kind of row transformation you did. And then when you multiply P on the left, it actually will play the same transformation on A. And then because A can be reduced to reduced row echelon form, so if you record such a kind of the row transformation, you will actually get this one, right? So this is P, right? And how do we find P? Okay, this P is actually the recorder, right? And then the method of finding P, I already played it over here, right? It's by actually this is a most basic but most hard method to find P. So you play this kind of trick, right? And then you writing down for each kind of row transformation, you're writing down this matrix, and then multiply all of that matrix together. So this is the P, right? So this is one method. Maybe intuitively the method could be like this. And then actually, because you can see P is the recorder, and then this matrix. Remember how do we got those matrix from those actions? It's by playing the same thing on the unit matrix, right? So actually, to find out this recorder, we can do things like this. We can do things like, so for example, you have this matrix, right? You have those ordinals of J1. Okay. You have this matrix like 1, 1, 1, 2, 3, and 3, 7, 11, right? Actually, in order to find the recorder, you just write a small dash line right over here, and then write a unit matrix right over here, right? And then you do the process such that this reduced to reduced row echelon form. And then after you're doing the process, your row transformation have already recorded right over here. So if you do reduced row echelon form, if you do some row transformation such that this reduced to the reduced row echelon form, just like right over here, which is 1, 1, 4 minus 1, right? And then a minus 1, 4. And then this matrix will automatically becomes the recorder right over here, right? It's minus 2, minus 2, minus 1, minus 1, 1, and 1 minus 1, 1. Minus 2, 1. So this is the method. Why is that? Because by doing the row transformation, you are actually multiplying p on the left of that, because the row transformation means left multiplying p, right? And if you left multiplying p such that this reduces to the row echelon form, and then this p, when multiplied on the unit matrix, will just become p itself. So that's why this part is p. So there are two ways to look to think about this fact. So the first way is that when you're doing row transformation, your action has already recorded over here. And the second way of understanding this is that when you do row transformation, it's the same as left multiplying some matrix P. And when you left multiplying the matrix P by the block matrix multiplication, this P will also multiply on this unit matrix, right? And then that's why the P will appear over here after you do all the row transformations. That's clear? Yeah. So this is a method of finding such P. And remember, this P is although this P exists, but this P is not necessary to be unique. Why is that? Because as you can see, there are a bunch of zeros right over here, right? So you can also multiply the last row by 2, but this is still the reduced rational form. So you can also multiply everything by 2, so you get 2 minus 4, 2, right? And it's still reduced rational form. So when your reduced rational form does not have those last 0, then your matrix is unique. But if not, then it's not unique. It's not unique. It is because you can do anything to 0, and you can actually add this 0 to any of them, which does not change the reduced rational form. So it is some case where one P is unique and one P is not. Okay. Any question? Okay, so yeah, so you can practice to find such a P where PA is reduced echelon form. Okay. Next, let's study what is rank. Actually, the rank is, I think it should be the most hard part of the matrix theory up to now. Let's erase this part. Okay, let's study the rank of a matrix. Okay, so let's define what is rank rigorously. Okay, if A is an n by n matrix, right? Then the rank of A is the number of leading ones in reduced row echelon form of A. Okay, this is a rigorous definition of the rank of A. So as you can see, it is very abstract. And what is the geometric meaning of that? Okay, so let's see some examples. So if I give you a matrix like this right over here, right? 1, 1, 1, 1, 2, 3, and 3, 7, 11. And you know that when you reduce to the reduced rational form, it will look like 1, 1 and minus 1, 4, right? Minus 1, 4. So what is the rank of this matrix? 2, because you have 2 leading ones over here, right? What is the rank? What is the rank of that matrix? 2. Also 2, right? Because they all have the same reduced row echelon form. So and then it basically tells you that whatever row transformation you do, then actually the A will keep the same rank, because A is only defined to be the number of leading ones. Okay, so what is the geometric meaning of rank? As you can see, when we study the reduced row echelon form, actually we want to study the all possible linear combination of row space or the linear relations of the columns, right? So it must have something to do with the row space. Okay, so what is the row space of this matrix looks like? As you can see, you can actually represent those row space by some parameters, right? Although the row space contains infinitely many vectors, but you can still use some unknown variables to represent a vector in it, right? Actually, what I mean is that any row matrices in the row space of that could be written as x, y, minus 1, x, plus 4y, right? So the fact is that if you think this point as a point in 3-dimensional space, and you collect all of those points together, right? What will you have, right? So if you think it as something in the 3-dimensional space, and then you collect all of those points together, as you see, you have already studied the curve 3, right? Because you have 2 parameters, and then it actually should be a 2-dimensional stuff. If you collect all those points, having those kind of coordinates in 3-dimensional space, it can actually gives you a plane. And this is 2-dimensional because you have 2 parameters. You have 2 independent parameters. So actually, what is rank? Rank is actually you can think the rank as the dimension of row space of A. Right? Okay, so this is a property. This is a how do we think about rank geometrically? And actually, the most interesting thing about this rank is that, okay, I'll erase this part. I'll erase which part should I use? Hard to decide. The most interesting is that the rank is also the dimension of the columns of A. But it's not clear from the definition, right? Is also equal to dimensions of column space of A. Maybe you need some proof upon this statement, but this is a fact that I tell you directly. If you want to prove, maybe you can check the notes. I might did some proof on the notes. So this tells you that geometric meaning of the rank is actually has something to do with the dimensions of the row space or the column space. So let's use this definition together with this geometric meaning to see to check some to see what is the rank of some matrices, right? Now let's do examples. Okay, so first matrix I want to tell you is that 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. Zero. What is the rank of that? Geometrically, do you have any intuition about what is the rank of that?
Is that one?
One.
Zero?
Zero? It's one, right?
It's one.
That's one. Okay, I'll explain that geometrically and arithmetically. So geometrically, what does that mean? You can look at the column vectors. You can also look at the row vectors, right? If you look at the column vectors, right? So that means I'll write something like E1, E2, and E3 as three-dimensional stuff. It is a basis. You will learn that in the future. Actually, there are something. Okay, and then this 1, 1, 1 is actually means that vector. Oh, it's hard to. Okay, this is. Okay. Okay, this is E1, E2, E3, right? And the 1, 1, 1, which I mean is E1, E2, E3 multiplied 1, 1, 1. It's actually equal to E1 plus E2 plus E3, right? Is this vector, right? Is this vector. You plus those three vectors together is this vector, right? And then you have three such kind of vectors, which is actually all the same. You have 1, you have 2, you have 3 same vectors. And then you consider the common space is by consider all linear combinations of those three vectors. Because those three vectors are actually the same, so A times 1, 1 plus B times 1, 1 plus C times 1, 1 is actually A plus B plus C, A plus B plus C, A plus B plus C, right? So all linear combinations of those three same vectors is actually consists of a line, which is a line over here, right? And this line is one-dimensional, so that's why the rank of that is 1. Okay, this is a geometric intuition for you to check whether it is 1. Okay, so how do we check it by using this definition? We do this process. We do the reduced fraction form, right? So what we do is like 1, 1, 1, 1, 1, 1, 1, 1, 1, and then we do like the second row minus the first row, the third row minus the first row, right? And you get 1, 1, 1, 0, 0, 0, 0, 0, 0. And this is the leading one. So in this way, your matrix only have one leading one, so the rank is 1. So the rank over here, rank over here is 1. Rank of A is equal to 1. Okay, that's clear. Question?
If the rank equals 3, can I just?
Yeah, it is invertible.
Oh, I'm just. I mean, like, if the rank equals 3, can I assume that it's like 3D?
Say again. If the rank is 3, can you assume what?
Can I assume like this like is 3D dimension?
Yeah. Like, yeah.
So
You can actually see if you draw that on the graph, it will actually span the whole space. Okay, I didn't talk about span. Okay. Okay, so this is one example. Let's see another example. Right? So, if I tell you that a rank of some matrix is 0, what is this matrix? Okay, suppose A is unbounded matrix. What is A? All of 0. Why is that? Then A is 0, 0, 0. Yeah, all 0. Why is that?
Because the rank counts the numbers as leading one. There's no.
Yeah, exactly. because if A is a non-zero matrix, when you reduce that to the reduced row echelon form, it will at least have a leading ones. So the rank of that can't be zero if it is not a zero matrix. So the only possible thing for A is the zero matrix. You can also understand this fact by geometric meanings of the rank. Because as you can see, if you collect all the column vectors of A, right? It should actually, when you do all that kind of combination, the condition tells you that it actually consists of a zero-dimensional space. What is a zero-dimensional space? A zero-dimensional space is simply a point, right? So that means you can't include any non-zero vectors. So which means all the column vectors are zero vectors, and all the row vectors are also zero vectors. So that's the reason why A must be zero. So the only matrix such that the rank is zero matrix. Okay. Let's do another example. Okay, suppose I give you a matrix like this. 1, 1, 1, 2, 3, and 1. Okay, 1, 4, 7. Oh, no, that's my word here. Okay, so what is the rank of this matrix? Rank of this matrix is equal to 2. Yeah, 2. Why is that? Okay. Okay, firstly, the rank of this matrix is not 0 because it's not a zero matrix. And it's also not 1. Because if the rank is 1, it means all these vectors actually only consist of one-dimensional space, which means all other vectors is a scalar multiple of some vectors. And it is impossible, right? So it's not 1. And 1 is 2 because actually you have 2 vectors. Firstly, you have 2 vectors in your three-dimensional space, geometrically, right? You have 2 vectors, right? You have 2 vectors, which is 1, 1, 1, and 1, 2, 3, right over here in your space. And actually, as you can see, the last column vector, as you can see, all of them are arithmetic cyclists. So the last column vector should be a linear combination of those 2, right? So actually, it means that this last vector should be a vector of some kind of maybe linear combinations of these 2, right? And maybe it's not that coefficient, but the last vector is actually kind of linear combinations of these 2. So all linear combinations of these 3 vectors are actually linear combinations of these 2 vectors, because this vector is already a linear combination of these 2. So geometrically, it means those 3 vectors can only able to span a plane, right? So the space that it actually can span is actually a plane. So that's why the rank is 2. But this is only the geometric understanding of this. We still have to do that rigorously. So the method that we find that rigorously is by we reduce row echelon form to that for that. And I already did that, right? Let me do that again. 1, 1, 1, 2, 3, 1, 4, 7. What we do is that the second row minus the first row and the third row minus the first row, what you get is 1, 1, 1, 0, 1, 3, and 2, and 6, right? And then you using the first row minus the second row and the third row minus 2 times the second row, what you get is 1, 0, 1, 1, 0 minus 2, 1, 3, and 0, 0. So you have 2 leading ones. So the rank of A is 2. So this is a rigorous way you should do. And this is the way you think in your mind. So, and if you don't have pictures, then you should do the by using this strict way to find what is the rank of it. Question?
And so you know the two vectors are 1, 1, 1, and 1, 2, 3 because those are the columns that the ones were in?
Hmm? Oh yeah, I just kind of draw the column space on the graph.
Okay.
Yeah. And then, okay. Any other question? Okay, so far so good. This is some examples of computing ranks of A. Okay, so. Okay, let's just put, let's talk about the two topics, which one should I push? It's also, okay. Okay, let me write these easy propositions first. Okay, so proposition for any matrix A, m times n, there exists two invertible matrices, namely P, which is m by n, and Q is also m by n, such that P times A times Q is actually equal to this is a m by n matrix. There is a sub matrix which is R by R. So this side over here is R. This side over here is R. So where R is equal to the rank of A. Okay, so this proposition gives you the actually the arithmetic expression of what is rank. So it actually means that you can do row transformations on A and column transformation on A, right? And if you allow to do row and columns, the easiest one you could get is actually this one. So why is that? Because firstly, if you only allow to do row transformations, the easiest matrix you can get is the reduced row echelon form, right? So, and then the rank is simply the number of the leading ones in the reduced row echelon form, like this. And then there's still something over here, like things over here, right? And now, if you allow to do the column transformations, then you are able to switch columns. And you are also able to use the columns to clean up all other dirty stuffs. Like if you have the reduced regression form right over here, so which is already PA. So P is a matrix, right? P is a matrix, right? P is a matrix such that PA is a reduced regression form. And then you can continue. And then what you do next is to use a column transformation to clean up this one, that one. Because as you can see, you can use leading ones. Because originally, when you're only allowed to do row transformations, you can only use this leading one to clean up the numbers below it. You are not able to use leading ones to clean up the numbers on the right of that, because you are only allowed to do row transformations. But now you are allowed to do column transformations. Then you are able to clean up those stars, right? And you are also able to switch columns. And then after that, if you record all your column transformations in Q, you will have PAQ is equal to 1, 1, 1, 1, 1, 1, 1. And then all of that is 0, 0, 0, 0. So you clean up all those stars and move these columns together, and you will get this one. So this is actually the rank in these expressions. Question?
I'm sorry, I didn't really follow that.
You didn't follow up the from here to here.
Yeah.
Okay. Here you got a reduced row echelon form, right? Okay, and then you can continue. Let me do an example to actually see how to get Q. Okay, originally I post matrix like this. So you know that okay, this is the nodes. This is equal to 1, 2, 1, 1, 2, 1. This is our reduced fraction form, right? And this is your A, this is your P, right? P is already equal to that. And now you do count transformation such that you kind of use this one to clean up all of those numbers and put all of them in a kind of combination. The condition tells you that it actually consists of a zero-dimensional space. What is a zero-dimensional space? A zero-dimensional space is simply a point, right? So that means you can't include any non-zero vectors. So which means all the column vectors are zero vectors, and all the row vectors are also zero vectors. So that's the reason why A must be zero. So the only matrix such that the rank is zero matrix. Okay. Let's do another example. Okay, suppose I give you a matrix like this. 1, 1, 1, 2, 3, and 1. Okay, 1, 4, 7. Oh, no dash line over here. Okay, so what is the rank of this matrix? Rank of this matrix is equal to 2. Yeah, 2. Why is that? Okay, firstly, the rank of this matrix is not 0 because it's not a zero matrix. And it's also not 1 because if the rank is 1, it means all these vectors actually only consist of one-dimensional space, which means all other vectors is a scalar multiple of some vectors. And it is impossible, right? So it's not 1. And 1 is 2 because actually you have 2 vectors. Firstly, you have 2 vectors in your three-dimensional space, geometrically, right? You have 2 vectors, right? You have 2 vectors, which is 1, 1, 1, and 1, 2, 3, right? Over here in your space. And actually, as you can see, the last column vector, as you can see, all of them are arithmetic sequence. So the last column vector should be a linear combination of those 2, right? So actually, it means that this last vector should be a vector of some kind of maybe linear combinations of these 2, right? And maybe it's not that coefficient, but the last vector is actually kind of linear combinations of these 2. So all linear combinations of these three vectors are actually linear combinations of these two vectors, because this vector is already a linear combination of these two. So geometrically, it means those three vectors can only able to span a plane, right? So the space that it actually can span is actually a plane. So that's why the rank is 2. But this is only the geometric understanding of this. We still have to do that rigorously. So the method that we found that rigorously is by we reduce row echelon form to that, for that. And I already did that, right? Let me do that again. 101, 123, 147. What we do is that let the second row minus the first row and the third row minus the first row. What you get is 1, 1, 1, 0, 1, 3, and 2, and 6, right? And then you using the first row minus the second row and the third row minus 2 times the second row. What you get is 1, 0, 1. 1, 0 minus 2, 1, 3, and 0, 0. So they have 2 leading ones. So rank of A is 2. So this is a rigorous way you should do. And this is the way you think in your mind. So if you don't have pictures, then you should do the by using this strict way to find what is the rank of a question.
And so you know the two vectors are 1, 1, and 1, 2, 3 because those are the columns that the ones were in?
Oh yeah, I just using I just kind of draw the column space on the graph.
Okay.
Yeah. And then okay. Any other question? Okay, so far so good. This is some examples of computing ranks of A. Okay, so okay, let's just put let's talk about the two topics. Which one should I push? It's also okay. Okay, let me write these easy propositions first. Okay, so proposition. For any matrix A, m times n, there exists two invertible matrices, namely P, which is m by n, and Q is also n by n, such that P times A times Q is actually equal to this is a n by n matrix. There is a sub matrix which is R by R. So this side over here is R. This side over here is R. So where R is equal to the rank of A. Okay, so this proposition gives you the actually the arithmetic expression of what is rank. So it actually means that you can do row transformations on A and column transformation on A, right? And if you allow to do row and columns, the easiest one you could get is actually this one. So why is that? Because firstly, if you only allowed to do row transformations, the easiest matrix you can get is the reduced row echelon form, right? So, and then the rank is simply the number of the leading ones in the reduced row echelon form, like this. And then there's still something over here, and like things over here, right? And now if you allow to do the column transformations, then you are able to switch columns, and you are also able to use the columns to clean up all other dirty stuffs. Like if you have the reduced direction form right over here, so which is already PA. So P is a matrix, right? P is a matrix, right? P is a matrix such that PA is a reduced direction form. And then you can and then what you do next is to use a column transformation to clean up this one, that one. Because as you can see, you can use leading ones. Because originally, when you're only allowed to do row transformations, you can only use this leading one to clean up the numbers below it. You are not able to use leading ones to clean up the numbers on the right of that, because you are only allowed to do row transformations. But now you are allowed to do column transformations. Then you are able to clean up those stars, right? And you are also able to switch columns. And then after that, if you record all your column transformations in Q, you will have PAQ is equal to 1, 1, 1, 1, 1, 1, 1. And then all of that is 0, 0, 0, 0. So you clean up all those stars and move these columns together, and you will get this one. So this is actually the rank in these expressions. Question?
I'm sorry, I didn't really
You didn't follow up the
like,
from here to here.
yeah.
Okay, here you got a reduced row echelon form, right? Okay, and then you can continue. Let me do an example to actually see how to get Q. Okay, originally I post matrix like this. So you know that okay, this is the nodes. This is equal to 1, 2, 1, 1, 2, 1. This is the reduced direction form, right? And this is your A, this is your P, right? P is already equal to that. And now you do column transformation such that you kind of use this one to clean up all of those numbers and put all of these one together. So let's just do that. To record the column transformations, I will write a matrix under this matrix. 1, 1, 1, 1. Right? Okay, the first thing I want to do is to clean up this guy and clean up those guys by column transformations. So it's the second column minus the first column times 2. And then I'll do the fifth column minus the first column, and then minus 2 times the second column, the third column times 2 minus the first column times 2, right? And then finally, I've got this matrix. By the second column minus the first column times 2, I clear up this guy, right? It's right over here. And then, okay, so and then the recorders is recording something over here. Right? And then the last column, the column 5, is subtracted by the first column, and then subtract by the third column times 2, and then subtract by the fourth column times 2, right? When the last column subtract the first column, this one goes away, right? It goes away. And then when continue subtracting the third column times 2, this 2 goes away. And when continue subtracting the fourth column times 2, this 2 goes away. Right? So this becomes 0, 0, and 0. And then my recorder here says that it's subtracting the minus 1 from the first column and subtracting 2 times the third column and subtracting 2 times the fourth column, right? So my recorder is over here. And then I want to arrange this to here, right? To make sure it is one on diagonal. And then the last column transformation I do is therefore, okay, is okay. So I just kind of switch this to here. So I will say switch second to the third, and then switch third to the fourth one. Okay, so finally what I got is, okay, so it's much smaller. 1, 1, 1, right over here, and all of that are zeros, right? And then you do the same thing here, so you move this part to here. So it's 1, 0, 0, 1, and 0, 0, 0, 1, and then minus 1, 2, 1, and then minus 1, 0, minus 2, minus 2, 1, right? Is this matrix. Right over here is Q. Clear? So that means if you continue multiply this matrix, 1, 0, 0, 1, 0, 0, 0, 1, minus 2, 1, 0, minus 1, 0, minus 2, minus 2, 1, it will give you this matrix. Is equal to 1, 1, 1, 0, 0, 0, 0, 0, 0. So this is the Q. The Q is just when you get the reduced direction form, right? And then you are using column transformation to clean up those stars, and then put all those ones together. And then you get PAQ is equal to this kind of form. Any question up to now? Okay. I think I expand in much details. So, okay. So now let's talk about how do we find the inverse of an invertible matrix. As you can see, when we talk about the invertible matrix, A is actually a square matrix, right? So firstly, if A is a square matrix, right? And if A is an invertible matrix, that means there should exist some matrix like P, such that PA is equal to identity, right? So what does that mean? That means actually the rank of A is equal to the size of A. So if A is n by n matrix, and PA is equal to the unit matrix, It's also an embedded matrix. And remember, the unit matrix is automatically a reduced row echelon form, right? So that means any invertible matrix have the reduced row echelon form, like equal to the unit matrix. So because any invertible matrix, it have the reduced row echelon form as the unit matrix. So that means we can using the method of finding recorders of how do we transfer A to the reduced row echelon form to find the inverse of A. Because you can see in this expression, P is exactly the inverse of A, because the inverse of A is defined exactly as the some matrix that times A is equal to infinity. So this is the method of finding inverse. So I'll just do an example for you guys to see how to find the inverse. And this should be the last thing in our class today. You guys want to give me a random matrix, like 3 by 3? Make a little bit smaller number.
0906.
0906?
Yeah.
Smaller.
What?
Oh, whatever. Okay.
4, 3, 2, 10, 0.
Okay. Okay. And then the method to find the inverse of that is actually you put a unit matrix right over here, or you can also put a unit matrix right over here. No matter where you put it, the thing we want is actually to recording the row transformation. How do we transfer that to the unit matrix, right? Okay, let's do the transformation first. As you can see, here's 2 series 6. So what I want to do first is that I want the second row minus 3 times the third row, right? So what I get here is 0, 9, 0, and it goes away, right? And 4 minus 30, so it's minus 26 and 3. And then 2, 10, 0. And then because I do the same thing to the unit matrix, the second row minus 3 times the third row is right over here, right? Okay, and then, it's not that bad because you have already 2 right over here. It is pretty good. Okay, and then I want to use this 9 to clean up all of that, right? How to clean up all of that? Because it just, okay. okay, let's do, okay, I want to make it to be 1 first. So the 1 next times the first row, I get 0, 1, 0, minus 26, 3, 2, 10, 0, right? And then it's 1 nice, 1 minus 3, 1. Okay. Seems something pretty bad comes up. Okay, never be afraid about fractions because you will you will see all of that when finding the inverse of our random matrix. Okay, and then you will use this one to clean up this 10 first, whatever I like. So the third row minus 10 times the first row, and also I want to clean up this. So the second row plus 26 times the first row, right? Okay, let's do the first one first. If I clean up this by 10, okay, I'll get 0, 1, 0. Okay, this is 2, 0, 0, right? And then this 9, 1 nice, because I minus 10 times R1, so it's minus 10 nice. 1, 1, minus 3. Okay, it's so far so good. And then we continue second row plus 26 times the first row. So the second row plus 26 times the first row, this clear to be 0, right? And then the second row times 26 plus the first row, so it's 26 over 9, right over here. Okay, so far so good. And then we want to make all of them to be 1. So this row times 1/3, and that row times 1/2. Not too bad, okay. So the 1/3 times the second row, and the 1/2 multiply the third row. What we get is 1, 1, 1 over here, right? So 1 nice and 1/3, right? So 26 over 27, 1/3 minus 1, and then it's 1/2. So it's minus 5 over 9, and it's 1/2. Right? And then finally, we just kind of switch this, right? So we just kind of, this goes down, okay, R2 switch with R3 and R1 switch with R2. So basically, this part comes down and this part goes up. So it's actually like 1, 1, 1, and minus 5 over 9, 1 over 2, 1 over 9, 26 over 27, 1/3, minus 1. Okay, so you get the matrix over here. This is a recorder, so this is a inverse of your original matrix. And then your conclusion is that this matrix is actually equal to right here. Oh, okay. So original matrix is over here, right? 0, 9, 0, 6, 4, 3, 2, 10, 0, inverse is equal to minus 5 over 9, 0, 1/2, and 1 over 9, 0, 0, 26 over 27, 1/3, minus 1. This is a way of finding the inverse, and then you will going to use that all the time in the future. So, okay, I think time's up. Any question about this? Good? Okay.